Lesson 1.6 is more limits. Now, I will say, I don't know if it's good or bad, we get pretty much the majority of our limits done in Unit 1. Now, it's good because we're getting a lot of them done. And you'll like a lot of the basic, there's a lot to do with derivatives. But the general concept of derivatives, I think you'll like. Okay? Now, the key is when we go in April to review limits, it's going to be oh wow. What did we do back then?
That's going to get tremendous.
And we might get some more, I'll try and get some limits review thrown in, but.
No, not the area.
So.
Area.
Okay, guys. Now that we have an understanding of limits and using limit notation, we can use limits to define continuity at a point. And I've already hinted a little bit at this and talked about it, but we're going to get official. So, continuity. That is something we use a lot with derivatives and integrals, is a function continuous. What I basically explained continuity as previously, like back in Algebra 2 or pre-calc, was, can I put my pencil down and draw the whole thing, right? Okay, I'm not going to have to pick up my pencil for a hole. I'm not going to have to pick up my pencil for an asymptote, but can I just draw the whole thing? Is it one connecting graph? Now, okay, so example 1. Use the graph below to complete the table. You should look for 3 conditions that are necessary to satisfy the definition of continuity. That is, what 3 conditions must exist in order for f of x to be continuous at a point x equals c. And yeah, we need to do the table down below first, and then we'll come back up and talk about our definition of continuity. Okay, so I have that here, but I was trying to make this big so we could see it, but I kind of need to have the graph on the same page, don't I? Oh, there we go. We'll do this right here. Okay, so x equals c, so they gave us some numbers, some key numbers. They're going to be mattering in this graph. So, first, find the function value if it exists for the given x value. So when x equals 9, according to the graph up above, what does it appear the function value is? I have 3.5 written down in mine. Okay, let's continue with x equals 9. So continuing across, find the left-hand limit. So the limit as x approaches 9 from the left is what? 3.5 again, yes? Because there's a piece of graph coming in from the left. Right-hand limit. Limit as x approaches 9 from the right. Does not exist because the graph doesn't come from the right, does it? Okay, that graph does not exist to the right, so D and E.
Like, it exists since it's filled in. It doesn't exist.
But the limit, the point exists.
Oh, but it doesn't, like, go on.
But the limit is at, I need a graph to trace to come into that point, and that doesn't
So
exist.
if it was an arrow, would it?
Like if there's an arrow going on past that point,
Yeah.
then we could, yeah. Yeah, I mean, like, if this graph just went on, well, something like that. Are you talking in that situation?
Yeah.
Then there would be a limit.
What if
right?
the point was an arrow? Like, instead of being a point,
Yeah, it would
then
work.
it would.
Okay, the general limit. The limit as x approaches c of f of x. D and E because
There's no right.
there's no right. In order for us to talk about the general limit, where it's not specifying left or right, this is where we go back to left and right have to agree. Is f of x continuous at x equals c? Technically, we should say no. Now, we can answer yes with a condition here because it's continuous from one side. Does that make sense? It's kind of a special case. I'm not sure why they start us off with this one. I know. Is it continuous? It's continuous one-sided only. So on one side, so I'm going to say one-sided only, yes. But in general, there's no right-hand limit, so in general we say no. It's just one of those weird, because it's the edge of the graph. That's the weird part about it. Okay, you ready for 4?
Sure. For sure.
Okay.
What?
Function value when x equals 4.
Ooh. Infinity.
Doesn't exist.
The function value is d and e because at x equals 4, there is no y value because of the vertical asymptote. What about the limit from the left?
Doesn't exist.
Yeah, why are we saying doesn't exist on the left?
There's no point.
There's a point. It stops at 3. It does not approach 4. Okay? What about the limit from the right?
Infinity.
That one's positive infinity because there's an arrow, and so it is going up to the right. What about the general limit? Okay. Does not exist again because we need it happening from both ways to exist. And is it continuous? No. No special case, no special answer. It's just not continuous because they're not connecting. Okay, 3. X equals 3. What's the function value? 9. Limit from the left. 9. Limit from the right. D and E. Are you wanting that answer?
No, it makes sense actually.
Okay. Now that you relook at it?
Yeah.
Okay. Okay. So then the general limit, D and E, because the limit from the left and the limit from the right aren't matching. Is this continuous?
No.
No. Okay. Right there, it's not continuous because the graph doesn't connect from both sides. Okay. When x equals 0, you ready? Function value. Okay, 6. Limit from the left. 6. Limit from the right. The general limit. Continuous. Yes. Okay. There's your true example of continuity. The limit from the left equals the limit from the right equals the function value. Okay, x equals -3. Function value.
Wait, never mind.
No, it's 5 because it approaches.
Function value.
Oh, function value.
What is that?
So I need a solid dot.
Oh,
-6.
Sorry.
In other words, if we're just looking up there where the rest of the graph is, there's a hole. So that function, if we didn't have that dot down low, then we would say this function value doesn't exist because there's a hole at that spot. The only reason we didn't say D and E here is because there is this removed dot here. Okay? Limit from the left. Limit from the right. General limit. 5, because when we're just talking a limit, it's just the limit from the left and the limit from the right have to match. Continuous. No. And the exception here, limit from the left, limit from the right, so the limit exists, but the function value doesn't exist at that point. And x equals -5. Okay, function value. We need the included point, yes. So -2. Left-hand limit,
-2.
-2. Right-hand limit, general limit,
-2.
they don't match, so D and E. Continuous? No. Limit from the left does not equal the limit from the right. Okay, guys. Definition of continuity. Okay. We've talked a lot about it, right? So I have 3 things written here. First of all, and this is being the official, f of c is defined. What do I mean f of c? F of c talks about the function value, right? So that's just saying that the function value is defined. So we can't have a D and E there. You can't have a hole. You can't have an asymptote. There, the function value is defined. Okay? That's one thing. The limit as x approaches c of f of x must exist. How do we get the limit to exist?
The left and right have to be.
Yeah, that's the shortcut, that's the fancy way of saying that the left has to equal the right, yes? Limit from the left has to equal the limit from the right. And, okay guys, the limit has to equal the function value. And the way to see that is that the limit as x approaches c of f of x has to equal the function value, which is f of c.
So all the numbers
Pretty much. Which is why we only had one continuous here, right? We only had one continuous because this was a funky graph, wasn't it? I mean, there was a lot of weird stuff going on here. Okay, so that's your definition of continuity. Anytime we talk about something being continuous, these are the pieces we'll come back to. And we'll refer to this on and off throughout the year. Okay. Got what you need on this page? Is it just me, or is this school a lot colder than it was yesterday?
I think it just gets colder by the day. Like,
Yesterday I was all like, oh, this is so comfortable, and today I'm frozen.
It's even.
But I don't know how warm it is outside either, so.
It's like
the library, oh my god.
Yeah, it's like 70 outside.
Freezing.
So
The library.
Our game is gonna be so nice. It's gonna be nice. It's gonna be like mid-60s.
If they don't mow,
I will tell you, last night sitting out in the sun, though, was a little warm at times, until the sun went under the clouds.
football.
So.
Did they mow the football?
Not
field
last
for the
night.
girls?
No.
No, it was bad.
Shane told me on Sunday that he was gonna mow it and then have to. That guy says.
It's supposed to be mowed today.
It is?
But, you heard the word.
Please
take
post.
your ankles, boys.
Okay, guys. Well, my comment to Corn last night, because there was a lot of kicks, I was like, man, these girls need to learn how to kick harder, And then, like, that was my thought last night, and Corn said, no, it was the grass. Like, I'm like, well, that makes me feel a little bit better, because some of these kicks these girls made, I'm like, really? That's it? Like, come on.
Don't judge us. It's going to be a fight tonight.
Oh.
But see, I know what to expect out of you guys. I hadn't watched girls soccer in 2 or 3 years. So,
What we're doing is way different than anything we did last year.
But it's
So
better.
I've heard.
It's not honest.
Okay, guys.
I think.
Limits. Well, limits told us where a function intended to go. Continuity guarantees that the function actually made it there. Okay? So, there are some different types of continuities. So, this is reviewing some vocabulary we've already talked about. We're going to talk about it a little bit more, but removable which is the word you've heard before this year, or point discontinuity. Okay? This is the idea right here. The limit comes from both sides. It's just a hole. So it's removable or it's point. You've also got one down here on this parabola. Okay? Now, a note I have written in my notes. This still falls into a removable or point discontinuity if, say, for instance, there's a point defined somewhere else where that hole is, that still falls into the same category. Okay, so you could also have the point defined elsewhere. So just kind of for reference there. Okay. Jump discontinuities. Okay, the definition they use here is that a one-sided limit exists. Think about you've got a limit from the left, a limit from the right, and you have to jump to get to the other portion of the graph. Okay, when we're talking jump discontinuities, we're talking of jumping from a point to a point, whether they be holes or filled in points, but it's a jump discontinuity there.
So that wouldn't be continuous because there's no like FOC value.
Correct. Well, or the limit from the left doesn't equal the limit from the right.
Doesn't that one of those holes have to be filled in?
Well, if it's defined to be a function, yes. Right now we're just talking about the different types of continuities. And so, I mean, the difference is here, this one's not a function, but we're just talking about the different types of continuities here. Does that make sense? Okay, so those are jumps. Basically, limit from the left doesn't equal the limit from the right. Okay, and then we have infinite discontinuities. Okay, this also falls into the category what you guys have heard previously as non-removable. And what have we always paired up non-removable with? Well, that is asymptotes, right? So at least one side of the limits doesn't exist. Basically, there's an asymptote happening somewhere along the way there. Okay? Okay. Continuing on to example 2. Find the points or intervals at which the function is continuous, and then the points at which the function is discontinuous on the interval -5 to 10. So we're going to talk about the points or the intervals where the function is continuous. And I have mine written in just interval notation. So, let's work our way from left to right. Where are we continuous? Did I spell mine right?
I know. I was
Yeah.
trying to spell
No, you don't want
Well, okay, but talk intervals for right now.
Okay.
So where do we, if we start at the left, what's our first interval of continuity?
-5.
Are we agreed?
Yeah.
-5 to -3. That is a continuous little piece, yes? Okay, now, again, I'm using interval notation. -5 to -3 is one interval. What's another, next interval?
-3 to +3.
No.
No, -3 to
2.
+2.
like 3. 3, no, 2.
Okay, so
What's happening?
let's talk about what's happening at 3.
Physical aspect.
Okay, it's not written in here, But you guys have been around long enough. You have figured out by using your clues, right? This is a vertical asymptote. So what's going to happen? It's going to run very, very close to 3 and not touch 3. Okay? So we can say -3 to 3 as long as we're using a parenthesis here. Just like we use parentheses at -3 because it didn't touch -3. Okay? Next interval.
3 to
3 to 5 because it's from asymptote to where? To that hole. Okay, now what?
5 to 7.
5 to 7. And then
7 to 10.
7 to 10. There's no arrow, so we're not going to go past 10. We're just going to say 7 to 10.
So then, would that be a bracket?
There's no point there, so I don't know.
When,
I don't have any of mine as brackets.
Would 7 be a bracket?
Because it's, well, I think depending on what you were doing, you could argue that 7 would be a bracket. I'm not sure about the endpoints, so at 10 and -5. We're more at this point just trying to list the intervals. And that whole bracket thing would be a different discussion. Because, well, maybe that 7, yeah. I'm not sure about 10. I'm not sure what we do there. Okay. The other thing it asked to list was points at which the function is discontinuous. So, discontinuities. See if you can spell that one. I don't know if I can sometimes, but I have the hardest time spelling continuous, like continuities. Okay. So, where was our first discontinuity? And what was that? X equals -3. It was a hole, and so we would call it a removable discontinuity, yes? I'm just going to write removable. What's my next discontinuity?
3. X equals 3.
And what is that? An asymptote. And that is a... Oh.
We messed it up.
No, I'll come back to it. Okay. I don't know if you guys said non-removable or not, but you did also say infinite, right? I know I heard infinite. It's also non-removable, just like this removable one is a point discontinuity. No, I was looking at, why do I have this? It starred, so I must have been confused when it was in the answer key. I have x equals -1.
What?
I have it as a whole and removable. But it's filled in our picture, isn't it? Okay, I'm going to skip over that one. Okay, keep going.
5.
What about 5?
Oh.
Okay, so a whole would be removable or point discontinuity. Anybody else?
7.
What's 7? A jump? Yeah. Jump discontinuity? I also have that written down as non-removable. It's not an asymptote though, so I'm not sure. And I guess that's the bell, so I guess I'm done, huh? Okay. Tomorrow I have a feeling we have a lot of notes to try and get through. We'll see.
2 pages for
Yeah. Okay. Of course, you're welcome to start working on homework at any point, but we will finish notes tomorrow.